we're just like really embracing it. So I'm going to be talking today about some of my research on the Queen Charlotte Fault, in particular, thinking about kind of fault zone structure, tectonics, and how those things are also related to earthquake behavior that we see along the fault. And so I'll maybe just start by saying that I'm a marine geophysicist, and when I finally, I'm gonna introduce the fault system a little bit. Hopefully some of you guys are familiar with the Queen Charlotte Fault. It's a really interesting fault system. It's not that far away from our backyard here. But I'll also be showing a little bit of marine seismic data, so both seismic reflection and refraction data, and I would love it if, I suspect we come from a lot of diverse geoscience backgrounds here, and so I'd love it if I show something that's a little bit confusing to stop and interrupt me, and that'll give me an excuse to like go off the schedule a little bit, which is usually a little bit more interesting. So I'm guessing for the Zoom folks, maybe I'll have a harder time with that. Follow up with me if you want to later. Questions. So I'll mention that this particular project that I'm going to be talking about is representative of a bunch of work that's been done in the last couple of years on the Queen Charlotte Fault with a big team of people. And so I'm not actually going to kind of name all the names here. I have like a whole other slide with logo. It gets wild. So, but I'll just acknowledge them and say thank you guys for all of the work. And I'll be showing some of the students on this. I'll be showing some of their work in this presentation. And then the other thing I'll mention before I've even shown you a map, for those of you who are familiar with the Haida Gwaii region of British Columbia, you might recognize one of the totem poles from that region. The work I'll be presenting here is it's not terrestrial work, but it's probably not far from the fishing grounds of some of the indigenous peoples who live in southeast of what is now known as Southeast Alaska and the Haida Gwaii Nation, the Tlingit, Shinshinaabe, and Haida peoples. So hope to kind of be integrating more of their perspective in this work as time goes on. Okay, but here we are. Just in case you need a reminder, we're down here. There we go. Okay. In this Cascadia region with the subduction zone just offshore, the Juan de Fuca plate just offshore. But if we work our way just a little bit to the north, we're going to experience a transition from kind of the compressional tectonics of the Cascadia region. Not that far away, we'll cross the exploratory junction and we'll get up into the sort of Queen Charlotte plate boundary up here. And so I like to kind of start out with a reminder of where the Queen Charlotte is, partly because it's not as famous as some of our other nearby plate boundaries. We have another subduction zone farther to the north in the Alaska subduction zone. I don't even have it included on this map, but I know there's a lot of folks here who've worked on the San Andreas Fault. But the Queen Charlotte is actually a pretty significant component of the sort of Eastern Pacific region and the tectonic structure. And so I'll be talking today about both kind of what we think about as being important processes that influence structure along the plate boundary, as well as earthquake behavior along the Queen Charlotte Fault. It turns out that it's not that different from the San Andreas in terms of its seismic potential. I'll talk about the earthquakes it's had in the last 100 years here in just a second. There are magnitude 7s and even 8 earthquakes on par with what we see sort of in our neighbor, the San Andreas to the south, but mostly because I think it's both in a remote location and it's primarily located offshore, sort of hugging the continental slope area, continental shelf, continental slope of this region. It's not as studied, right, as the San Andreas Fault, which makes it a really exciting place to work. And so today I'm going to just try to give you a little bit of an introduction to the margin for those of you who maybe aren't intimately familiar with the Queen Charlotte Fault, specifically earthquakes and kind of plate boundary dynamics. And then I'm going to talk a little bit about this new project that I've been involved in. We've kind of lovingly named the TUCS project. This is an acronym. If I have any Canadians here, Scott's pointing to his head, right? So this is a Canadian word for hat, I think. No, I'm just kidding. Right? Yeah, there we go. We have at least 2 TUCS in the room. So I'll tell you what this acronym is for in a second. But as I mentioned earlier, specifically, this is a marine seismic effort to try to better image this complicated and interesting plate boundary represented by the Queen Charlotte Fault. For the kind of full crustal and even into the mantle scale of both the Pacific and North America plates there. And then we'll sort of think about what we're learning from this new information about margin deformation and fault architecture. Okay, so if you are not super familiar with tectonics or earthquake processes or fault zone processes, but you've taken a Geology 101 class, you might have heard of the Queen Charlotte Fault. I think this is its most famous reference in Geology 101 textbooks. And what the figure is on the right here, this is a map. So just to orient, here's Haida Gwaii. We're working our way up into Southeast Alaska as we move north. So this is all the Pacific Plate again. You kind of get a hint as to the morphology as you transition across the continental margin here. And what the red stars are, you can see them are a series of magnitude 7. There's even a magnitude 8 earthquake in here that have happened in roughly the last 100 years or so along the Queen Charlotte Fault. And the probably most famous thing that the fault has done is associated with this magnitude 7.8 1958 earthquake. It's this guy right up here that happened kind of in this northern extent of the Queen Charlotte Fault. It's a large earthquake, and as is pretty common in this region where we have dynamic, sort of glacially influenced terrain and places where we have significant river systems putting lots of sediment into the marine system, there was a landslide triggered by ground shaking of this earthquake that generated a rock slide, some of which landed in Lituya Bay. Okay, and so this is now an aerial image of Lituya Bay. This is from not just shortly after 1958 earthquake when this was taken. And what you see along the edges of the Lituya Bay Fjord here are locations where the trees have been removed from the tsunami that was triggered by that landslide from the magnitude 7 earthquake. And so I like introducing the fault in this context. So this particular tsunami was probably, correct me if anybody knows this to be wrong, please tell me, but I believe the largest documented tsunami run-up of any tsunami that's ever occurred and been observed and documented kind of in modern times. 1,700 feet run-ups around Lituya Bay. I have to put the number on the slide because I always question myself when I don't put it on the slide. I'm like, am I off an order of magnitude? But no, that's the height at which trees have been removed along the edges of Lituya Bay. And so although there were not any people who were actually hurt, to my knowledge, because it's such a remote location, this is an interesting example of the kind of exotic multi-hazards that places like Southeast Alaska and the Pacific Northwest where we live are associated with when you start considering significant ground shaking from large earthquakes triggering secondary hazards like landslides and tsunamis. And so Lituya Bay is kind of a famous example of one of these landslide triggered tsunamis. These events were really common in the 1964 earthquake in Alaska and along south central Alaska, subduction zone up there. And there probably have been thousands of these, that some of which may have been observed, some of which haven't, associated with Queen Charlotte Fault earthquakes across the region. There's so many of these glacial fjords present. Okay, and so I'm back at this earthquake figure. Oops. Sorry, I need to be careful about that. There we go. I'm back at this earthquake figure. And you can see that this older 1958 earthquake was a magnitude 7.8. There's a series of other magnitude 7s along here. There we go. Okay. And before I move on from this, I pause and make the point, as I said a minute ago, the Queen Charlotte Fault, as the plate boundary fault between the Pacific and North America, it's slipping quickly. It's slipping 5 to 6, almost 6 centimeters a year in places. I'm going to talk to you a little bit later in the presentation and try to make the point that we think probably most of that slip is accommodated on like a single fault system, which is different from some of the other big strike slip systems across the globe, like the San Andreas, for example, where we have multiple faults that are accommodating that plate boundary strain. But we also have really big earthquakes that are associated with that kind of slip, okay? And so the other earthquakes of note in this list, in 1949, 1981 is the largest earthquake recorded in Canada in modern times. And then these two events, the 2013 magnitude 7.5, this guy right here, and the 2012 magnitude 7.8, you'll notice those are pretty recent events. And these two earthquakes are really what motivated a lot of the work that we've sort of followed up on in the last few years. And this is what's kind of being shown over here on the left. If you look closely, if you're familiar reading focal mechanisms, I bet some of you guys in this room are, What you might notice in looking at the red mechanisms that are represented on this figure is this magnitude 7.5 to the north kind of looks like a strike slip fault, as you would expect to cross the strike slip plate boundary like the Queen Charlotte Fault. But the one to the south is a thrust mechanism, okay? And so this is a mechanism where you have, a shallow dipping thrust fault accommodating most of this magnitude 7.8 earthquake slip. To the west, you have actually normal faulting earthquakes. This is almost looking a little bit like outer rise earthquakes at a subduction zone. And so if all I had told you today was like, this is a strike slip plate boundary, you should be scratching your heads and saying, what? Wait a minute, how is a magnitude 7.8 earthquake being accommodated on a thrust fault? Okay, and so this is another one of the really cool and interesting things about the Queen Charlotte Fault is that the subtle change in the strike of the fault as it goes from south to north leads to an amount of compression, specifically in that southern region, that we've kind of known about for a long time. Really smart people have been studying the Queen Charlotte Fault well before these earthquakes happened. But these recent events kind of reinforce this idea that there's some amount of convergence that's got to be being accommodated along the plate boundary. In this case, via a rather large earthquake that generated a very small tsunami in 2012. And that kind of systematic change in higher convergence in the south, transitioning to sort of lower convergence or more normal strike slip behavior in the north, makes this a really interesting place to sort of study that tectonic expression along the fault, okay? Okay, so this is, I'm not gonna spend a ton of time on this, but this is a nice image that tries to illustrate what I just said with some like graphs where we're trying to take plate boundary estimates, and we're looking at the strike of the fault. And so in particular, just to orient you guys here, this is latitude on the x-axis of all of these plots. So you can think about south down by Haida Gwaii, to north, closer to like Sitka, Baranof Island region. And so what this is trying to show you is if you take plate boundary motion or plate motions, you can use your favorite plate motion model to do that. And then you take sort of some estimate of the orientation of where the fault is, you can identify a transition from high compression in the south. In this figure, it's as much as 20 degrees estimated of the angle of obliquity or angle of convergence in the south on the fault, down to something closer to zero, closer to strike slip behavior in the north. This particular set of figures is from a paper from 2015 by Anne Trehu et al. And this work has been updated in more recent times. This looks completely different, but it's kind of saying the same thing. And so I'll walk you through it here. So this now we're looking at a map instead of a latitudinal plot. But what the reds are showing you are the amount of convergence, okay? And the blues are showing you actually little zones of actually extension. So this is using a slightly different plate motion model and a much more high resolution estimation of where the fault is actually located. And so that's what gives us these little wiggles, very little variations in extension and compression, especially in the north. But the main takeaways from this, looking at it this way, is that we have a pretty significant, consistent compressional, kind of oblique compressional zone in the south down by Haida Gwaii that transitions into something more variable, but probably more similar to like what we think of as being associated with strike slip faulting without necessarily that transpression or that compression in the north. This is from Brothers et al. So these guys in particular, I'll show you some of this data in a little while, but they used really high resolution bathymetry mapping to come up with sort of the level of detail for where the fault's located and how much compression or extension we would expect to create this figure. Okay, and so folks have been observing this before and then certainly after these recent earthquakes have come up with some ideas for how sort of the tectonic and deformation expression of the fault might evolve as you go from this highly oblique zone, this compressional zone in the south, to something more kind of strike slippy in the north. And so this is one example of some cartoonified tectonic deformation models where you have features like the Queen Charlotte Terrace, okay? And so this is kind of the portion of the continental slope offshore Haida Gwaii. It starts to look a little bit like an accretionary prism of a subduction zone. I'll show you some examples of that, the real data, in a minute. You have the terrace being associated with sort of deformation, maybe shortening of the Pacific plate to accommodate that compression in the south. That evolves, whoopsies, sorry everybody, okay, that evolves as you go to the north into kind of an intermediate zone where you have maybe some crust faulting or even some wrench kind of faulting, maybe reactivated structures from the south that continue to accommodate a little bit of compression to sort of the north, and then eventually something simpler where you have this kind of more normal pure strike slip behavior the farther north you go. Okay, and so these are the kinds of ideas that motivated the group of folks that I've been working with to say, well, this is cool. We haven't really been able to see this. We haven't been able to use geophysical imaging, at least seismic data, to look for these kind of structures and ask the question, you know, is this what's going on? Can we confirm this? Kind of based on kind of cross sections through the lithosphere on the Pacific and North America side. And what can we learn also about how this type of transition might be influencing some of that earthquake behavior? So not just how a thrust earthquake could be accommodated in the south and a strike slip earthquake could be accommodated in the north, but what about these subparallel faults? Are they still active? Are they generating earthquakes? How, you know, do we expect the sort of vertical strike slip fault to still be active to the south? And then how do the material properties change, which we also expect to be influencing earthquake behavior? Is this actually continental material next to, continental material next to oceanic material, or do we have something more complicated going on? So these are some of the things we're really interested in thinking about. I want to move on and talk about some of the new data that we have in association with work. Before I do, I'll mention that there's also some sort of competing ideas about how this southern portion of the margin is actually, you know, constructing or accommodating this compression. Is it purely through the crustal shortening, as might be being illustrated in this cartoon? So the Pacific plate's deforming, and there's maybe multiple, actually sort of higher angle thrust faults that are occurring. Or, let's see here, are we actually dealing with a situation where we have something that looks really a lot like a subduction zone offshore Haida Gwaii? And I think if you looked at the mechanism of the 2012 earthquake by itself and the distribution of aftershocks sort of within the Pacific plate, this is kind of a complicated figure, but this might be the model that you would come up with, where you have the Pacific plate actually under thrusting portions of the continental side of the plate boundary. And so in this cartoon, if you guys can kind of follow how it works, this would be the Queen Charlotte Terrace. This would maybe be the sort of terrestrial portion of the Haida Gwaii Islands out here. And this would have that magnitude 7.8 earthquake being accommodated along a shallow dipping thrust fault that would go under, that would be representative of the interface between the Pacific and the North America plates. And so sort of asking the question, you know, which of these two models is more accurate is another thing that we're interested in doing with some of the new data that we have. All right. Okay, so I have a couple things up here that I've been talking about that make the Queen Charlotte fault interesting. One of them is this systematic change from north to south in the amount of obliquity. Another one is you know, this idea that there's probably been some way that strain has been partitioned in that highly oblique zone. We see that as evidenced by the type of earthquakes that we've observed along the southern part of the margin. And so how that strain partitioning is happening is interesting. A third thing that makes the Queen Charlotte fault really cool, is I'm explaining numbering up here in this slide, is the fact that if we zoom in and we use some more modern data to look at the morphology of the margin, so just what is the shape of, in this case, the seafloor across the fault zone, we see some really cool things about the fault, especially as compared to maybe other big plate boundary strike slip faults. Okay, so what you're looking at in this figure, this is the section of the margin. I'll just tell you, I don't have a great key here, but this goes from kind of the Alaska-Canadian border on the southern part of this margin. So this is sort of near the Dixon entrance, if you know where that is, just north of Haida Gwaii, up to kind of somewhere just south of Sitka up here. Okay, so it's kind of a central chunk of the margin. And what the colors are here, this is where the marine geophysicist gets super excited. And this is high resolution multi-beam bathymetry. So you can think about this almost like LiDAR data. It's just a little bit lower resolution than like really awesome 1 meter LiDAR data. It's probably greater than a couple of meters resolution. And so this is time consuming to collect this kind of multi-beam data. But if you look closely, it has some really amazing morphological structures that are imaged just looking at the seafloor by itself. And so in particular, if we zoom in actually in this box kind of up in the northern section, this is what we're looking at on the left here. Okay, and so I think I have another zoom in kind of this section of this portion of, this is a sea valley or a kind of glacially formed outwash channel. So this was probably formed during the last glaciation 10 or 12,000 years ago. And what we can see if we look really closely at sort of the edges, it's called the Jacobi Sea Valley, is that where the Queen Charlotte Fault crosses this sort of glaciated terrain, there's really clear sort of piercing points or offsets in sort of the margins there. And so if you are used to looking at almost any kind of geophysical data, but especially multi-beam bathymetry data, you should look at an image like this or an image like this and say, well, that's an artifact. That must be like not real. It was something about the way the ship crossed over. But this indeed is not an artifact. It's, oopsies, there we go. It's real. It's a real feature, and it's a place where the kind of the edge of that sea valley has been offset by about 900 meters in this case, if you're really careful in how you measure it. And if you do some math and you work this out, what you find is that that type of an offset over that type of time scale should account for really all of the plate motion between the Pacific and North America plates. And so that's really interesting and cool. It implies that this is sort of at the northern end of this kind of extent of the fault that I'm talking about here, but it implies that indeed there's really like one main structure. And if you extend this down deep into the lithosphere, you might even start to ask yourself, well, does that mean that like all of that earthquake behavior and all of that strain is being commented on one main feature? There's like no deformation on either side of that fault. Is it perhaps even the boundary between the Pacific plate and the continental plate? Should we see continental materials right next to oceanic materials? I don't know. It's not what I would have expected based on my experience thinking about earthquakes along the San Andreas Fault, for example, where actually most of the earthquake behavior is happening in kind of complicated accreted continental materials. So this would be really different from that. And it's really cool to think about. Okay, so here we are, finally got here. So this is where, these are my 3 interesting things that I have listed up, my 3 interesting features of the Queen Charlotte Fault that makes it a cool place to study tectonics and earthquake behavior. Now we're gonna put our tubes on, and we're gonna think about how we can collect some more modern seismic data and try to gain some new insights into sort of the crustal or lithospheric structure, so the deep structure of the margin, and try to see some of these things in more detail. Okay, so long-awaited explanation of the acronym. This is the Transform Obliquity along the Queen Charlotte Fault and Earthquake Study. Made it work into an acronym. First thing you need to know if you're a marine seismologist is that you need good acronyms. Maybe that applies to other fields in geoscience too. And so we're interested in thinking about the specifics of the deformation structures that might be present along the Queen Charlotte Fault in these different transpressive regimes, okay, these highly oblique in the south versus low obliquity in the north. We're interested in kind of asking more questions about, well, what are the actual rocks and the associated rheologies along those different sections that are probably important for controlling the earthquakes there. And we're also specifically interested in thinking about that strain partitioning question in the far south. You know, can we differentiate between whether we actually have, with that 15 to 20 degrees of obliquity, we actually have underthrusting of the Pacific beneath portions of North America, kind of wild along a transform plate boundary, or is there maybe a lot of crustal shortening that's accommodating that transpression? Cool. Okay, and so this is what the Twig study looks like in experiment map framework. Okay, so one thing I'm showing in this figure, I'm showing a lot of like large scale maps of the Queen Charlotte Fault. So hopefully by the time I'm done, you guys will be familiar with all of these geographic regions. Here's Haida Gwaii. This is Prince of Wales Island. Okay, so I don't have it shown here, but the second of the two large earthquakes, the 2013 earthquake, happened kind of right offshore Prince of Wales Island up here. And then sort of Sitka is right to the north of us here. This is Baranof, the tip of Baranof Island. So what you're looking at in this station map is a bunch of transects that are all 2D transects, but are configured in a way that we're hoping to be able to image different parts of the margin and start to answer some of our science questions in the context of this sort of specific imaging targets. And so all of the yellow lines that you're looking at are places where we're going to go out and we're going to collect multi-channel seismic reflection data. Okay, for those of you who aren't thinking about this all the time, I'll remind you what that looks like in a minute. So the data that uses bouncing seismic waves to image layers in the subsurface. Where you see, hopefully you guys can see it from where you're sitting, but where you see little red dots here, this is going to be places where we also deploy seismometers on the seafloor that allow us to get really large offset recordings of active source shots that allow us to image the velocity structure of the subsurface as well. Okay, and so we don't have that capability on every single of these two-dimensional lines, but a lot of them have those little red dots to go along with it. And so today I'm really just going to be, this is a big effort. This is why all of those names were on that first slide. I'm going to mostly talk to you in sort of the results component of this talk about a line way in the south. Okay, so this is, I'll refer to this as line 3. And this line in particular was organized to cross through kind of the central zone of that magnitude 7.8 thrust rupture event from 2012. And I'll also show you some images of a line way up to the north. So this is line 12, and this one went right through the epicenter of that second event, that magnitude 7.5 strike slip earthquake. Okay, so those are going to be the two data sets that I share with you today. Okay. And before I do that, in case you're getting bored, every talk needs some kind of animation these days. So I'll talk at you while I show you this. But what this animation is showing you is actually the track line map, the time series of where the Marcus G. Langseth sailed in 2021 in order to collect this data set. So it's still going. It took us about a little over, like close to a month and a half to do all of this work. It went up and down and zigzagged all around. The way that this type of data is collected is you get out there, usually it takes a little bit of time to deploy the instruments that you're going to use to listen for the seismic energy. And then at some point you have to deploy gear off the back of the ship. That takes a little bit of time, and then you spend a bunch of time shooting, and then you go home. And so that kind of explains the complicated pattern. While the Langseth was working, another ship, I was actually sailing on the Coast Guard, the Canadian Coast Guard vessel, the John B. Tully right here. And so I was out there working with the team to try to deploy and recover 123 ocean bottom seismometers in order to do those long offset recordings. And so it was a lot of work. It was really successful. There was over 4,000 kilometers of new data collected. I'm going to be working on this for the rest of my life, probably. At least I hope so. But it was really exciting. One more image here to just wake you up if it's late in the afternoon. And so I'm guessing that many of you guys are familiar with what active source marine seismic data is, but just in case you're not familiar with that, this is sort of the heart of what we rely on for marine seismic imaging. We use what's essentially an artificial earthquake. So it's smaller than any earthquake that we would record with a typical seismic array, but it's a air gun array, started again at the beginning, that you're looking at right here. And if you look really closely, eventually you'll see sort of what looks like sort of fuzzy, there it goes, water that comes up. So this is a compressed air that's sent from the ship into the air guns, makes a bubble, and then that bubble collapses from the pressure of the water. And that collapsing bubble produces a seismic energy that's sent through the water column and eventually couples into the ground. And so if you think about what I just showed you, the map of the ship going up and down the margin, and then you kind of look and see, this is the view from the fan tail of the Langseth looking out at the air gun array. This is pretty much what we did. for a month and a half while we were out there on the Queen Charlotte margin. What you're looking at here is hopefully you're not going to see but these are sort of lines that are connecting both the air gun array and a hydrophone streamer that's also being thrown by across the back of the stream. That's listening for sort of near offset returns. Okay. All right, and so I teach a lot of undergraduates at Western, and so this was my like fun cartoon trying to illustrate some of the work that we were doing. I'll have a little bit simpler version of this on the next slide, but here's the landslides at the top. Here's the Tully busy over on the left. And so while we were out there on the margin collecting data for this TUTS experiment, we had a 15-kilometer streamer deployed. And so that hydrophone streamer is going to be one of the two types of recording devices that we use to create these seismic images. It is a linear array of hydrophones, okay? So kind of like mini seismometers, but capable of observing little pressure waves that are traveling through the ocean, acoustic waves. There's thousands of instruments that are stringed along that 15-kilometer array that are organized into little groups of instruments. I want you to pause for a second, think about 15 kilometers, okay? It's like longer than most of us would care to go for an afternoon run, probably, or it might be longer than your commute home for some people. So it's a really complicated endeavor, and it's really amazing, I think, to think about the scale of this. It's a really valuable data set that ends up being collected. And so that streamer data in particular is what we use to try to listen for waves that are generated at the air gun array and that bounce off of layers in the earth where there's some change in the density properties or the speed at which the waves are traveling. So density and sound speed are what's going to allow waves to bounce really efficiently off of sediment layers or maybe the basement or sometimes even beneath the oceanic or continental basement rocks. These wiggly orange lines, so these are now waves, right, that are bending through the subsurface. Okay, we need to have farther offset listening devices in order to kind of make the geometry work to listen for refracted waves. And so this sort of ends up giving us two different types of data. The reflections give us kind of a cross section of specific structures and unconformities within the subsurface, whereas the bending waves, the refracted waves that are recorded on ocean bottom seismometers are going to give us information on the physical properties of the rocks themselves and specifically the seismic velocity structure. So we're going to use some kind of fancy processing to provide images of subsurface structure using these two methods. The reason this is one reason I recognize Wally. Well, yeah, so we were deploying lots. I think I have another slide here showing you the actual instruments we use. These are the actual OPSs we're using. But the ship's crew on the Tully thought they looked just like Wally. And so for now on, I'll be just calling them Wallies for the rest of my career, I think. But this is just a picture of some of the technology. This is a reel of that 15-kilometer hydrophone streamer. It may not be impressive, but it's pretty impressive when you're standing next to it. It's especially, it gets like stinky after it's been in the water for a month. So it's impressive in that way, if no other way. And this image at the top is another sort of simpler, more textbooky version of what I was just talking about, with reflections being recorded on the hydrophone streamer that are bouncing off of layers in the subsurface, and then refractions that are bending through the crust and upper mantle. All right. Cool. All right. Okay, so I'm going to move kind of fast through this. I have just one data figure here of kind of the rough data that goes into some of the modeling procedures we use. And it's a little bit complicated, especially for students here. I love talking about this. So if you have interest in time afterwards, I'd be more than happy to go more slowly through what this slide is trying to show you. But this is a receiver gather from an ocean bottom seismometer that's recording something, something like 700 shots of the Langseth crossing the Queen Charlotte Fault. And so, I know it's a little bit small, but this is just the seafloor shape along this line. Okay, so if you just looked at like the shape of the seafloor, this is what you'd look at. This instrument right here is SO8, it's kind of right in the middle of the line. And essentially what we're doing is we're taking a time series. So these are little seismograms that are all stacked up for every single one of those 700 shots. And we're organizing them with the 0 time at the time of the shot, and then some delay time before we see energy coming in that tells us the travel time of those waves through the subsurface, okay? And so if you can pick that travel time, you can use that time to model the seismic velocity structure of the subsurface where that wave traveled, okay? And so we use this in a sort of a nonlinear inversion, and we come up, this is seismic tomography, and we come up with a seismic velocity model. I'll show you what this looks like in a second. But even just looking at the data, if you kind of know what you're looking at, you should be able to pick out different types of waves that are traveling from different layers based on sort of the slope at which they're arriving across different offsets. And so this would be this blue dye, this would be the waves that just go straight from the air gun array to the ocean bottom seismometer through the water. The PGs are the code we use for waves that enter into the subsurface and refract through the crust and the sediments above the crust. PNs, meanwhile, with kind of the highest, in this case, slope sort of in this direction, are waves that are traveling pretty fast. And so these would be like 8 kilometers a second waves that are probably making it into the oceanic mantle. Okay, so the higher offsets you go, this is, I'm just gonna show you this really quickly. This is that same data set now shown as a ray plot. Okay, so each of those, this is the same sort of offset direction. This is where the OBS would be located. And so these might be with rays that are traveling through the upper mantle. You can see that the higher offsets go deeper into the earth. Okay, so that's kind of the basis for what some of these images I'll show you, what the basis for that is. Okay, all right. I'm going a little slow, so I'm sorry. I'll probably speed up as time goes on. I wanted to mention though, mostly for the benefit of any of the students that are here, that this project also had a passive source, so just an OBS deployment for a year to listen to earthquakes. And this component of the study was specifically organized to really incorporate students in every part of it. And so I have some photos here of undergraduate students who sailed with us, specifically on the recovery cruise for an array of 28 ocean bottom seismometers that were also located up on the fault while we were doing this work. Most of these guys were looking at our Western Washington undergrad, but we had students from a couple different universities join us, and they really ran the cruise for this component of the project. They did everything from recover the OBSs to collect multi-beam bathymetry data all up and down the margin while we were out on the ship. And they were watch standing, but they were also like really engaged with all of the activities on board. And so at the end of this presentation, if I leave enough time, I can talk a little bit about other opportunities for students who are interested in going to sea and helping to collect marine geophysical and other types of marine science data on these big ocean going research vessels. Okay. All right, so I've already mentioned, I'm going to mostly be talking now about what these seismic images look like along line 12, so in the northern part of the fault. I'll get to that second, actually. But first, I'll start with images along this highly oblique portion of the margin just offshore Haida Gwaii. Okay, so just as a reminder, I might refer to this as line 3, but this is a cross-section through the Pacific and to some degree North American places, you sort of just barely sample the margin west of the fault with these profiles, that was specifically located in a place to try to target this question of like, how is obliquity being accommodated along strike? Okay, all right. Here's a geologic map for you guys. I didn't really leave, I'm gonna go quickly through this, but I'll also mention just, if you find that you're like, wait, Emily hasn't really talked about what we even think that continental crust is gonna be made of here, I'd be happy to go through this a little bit more slowly, but this is a geologic map of this area, okay? I think this particular figure is funny because I always have a little trouble like orienting where the land ocean boundary is, but this is gonna be that line 3, this is gonna be that line 12, okay? So the 2 lines I'll be showing you. And so what we're gonna be, if we see pieces of the continental side, what we're really gonna be seeing are our slivers of Rangalia and Alexander terrains, okay? And so these are accreted complexes, part of the insular terrains. They're complicated formations with a lot of different types of volcanic and siliciclastic and even carbonate rocks in them. And so it's a complicated zone that's been sort of tacked on to and modified on the Western Cordillera for the last definitely tens of millions of years. And I bet some of you guys might know about this even better than I do, but it's definitely a part of the story here. Okay.
All right, and so once again, here's this line. I'm going to be showing you right through. These are the aftershocks of that magnitude 7.8 thrust event. Okay, and I'm going to start by showing you images of what that reflection data looks like crossing this line. Okay, all right, and so we like to do this when we're showing these reflection images. This is sort of a color map of the bathymetry. I'll show you this bathymetry in a couple different ways, but what you're looking at on the far right here is this is sort of the steepest portion of the continental slope. And we're going along what's also referred to as the Queen Charlotte Terrace here. So this is Haida Gwaii, sort of the terrestrial portions of Haida Gwaii would be on this side. We're well into the Pacific sort of basin on this side. And so if you're not used to looking at seismic reflection data, what we like to do is look for discontinuities in reflectors. Remember, these are telling us something about sort of the material properties, variations in the material properties where we'd have seismic waves bouncing off of layers. And so where you see discontinuities in those layers, we sometimes can interpret those as the location of faults. We can also look for folds and evidence of deformation. Not surprisingly, this Queen Charlotte Terrace zone is highly deformed. Then there's some evidence of active thrusts within the Queen Charlotte Terrace zone. There's also some deeper structure in here, though, that's really intriguing. Okay, so for thinking about this in terms of a reflection profile crossing through that highly oblique portion of the margin, we can identify a active deformation faulting on the west side of this profile, significant convergent deformation as you transition into the terrace. And then you might say, well, where is the Queen Charlotte? So here's the Queen Charlotte fault right here. So if you picked out sort of a near vertical location where like the seafloor morphology or the seafloor expression of the fault would be, it would be way over here in an interesting place where you can see a subtle change across the Queen Charlotte fault, but we're not, at least with the reflection data, able to learn much about the fault zone itself, except that it seems to be a transition from really significant deformation on the west to something not very deformed, at least in modern times, within this little sort of sedimentary basin on the east side. Okay, cool. So that's pretty interesting stuff. Other things in this figure I can explain. So it's a little bit, I don't know if you guys can see sometimes when we animate things, it's hard to see, but this reflector right here, this is probably the Pacific Moho. Okay, had it labeled. And there's hints even of another reflector that's sort of extending underneath the terrace. Okay, so this is maybe the first hint that although certainly there's shortening going on in this portion of the margin, there may also be some evidence of underthrusting of that Pacific plate there. Okay, all right, and so I'm gonna hop forward. I have some zoom ins here of what these structures look like. I mentioned this already. It seems like a transition and deformation across the Queen Charlotte fault, but really a lot going on just west of it. Now I'm going to show you, I'm just looking at the clock and realizing we're getting close on time. I'm going to show you results from the refraction imaging. Okay, so now the colors here are seismic velocities. So they're telling us something about sort of the density structure and the different types of materials that we have in that same profile, right? And so for those of you not used to looking at seismic velocity structures, don't worry too much about this. If you take my word for it, if we take a profile right through sort of this far western portion, we're seeing velocities that are really consistent with what we would expect. Sediment on top of oceanic basement, eventually getting into something closer to the oceanic mantle seismic velocity structure. On the east side, however, we're seeing evidence of what looks to be pretty nicely deformed and pretty fast seismic velocities, maybe consistent with parts of that oceanic basement being thrust up and maybe almost like a nape-like structure or a imbricate thrust fault structure. So this is that seismic velocity expression of what we were looking at in the seismic reflection data, but now we're seeing sort of evidence of that high density material going up into some of those big folds. We see a transition from kind of a low, this is the Queen Charlotte fault now. We see a transition from kind of a section of relatively low velocity, probably porous, maybe some unconsolidated sediments up there, material, to really fast seismic velocities just east of the fault. So there's definitely, again, evidence of sort of a change in the structure on either side of that kind of vertical expression of the Queen Charlotte Fault. Okay. All right, so this is actually from a paper that where Roland was using gravity data, but this is actually pretty consistent with a few caveats with how you would interpret the margin just based on the gravity structure alone. Okay, and so where you have under thrusting, okay, of something that seems to be consistent with the oceanic moho, at least under the Queen Charlotte Terrace, we're not really imaging this portion under the Haida Gwaii Islands very well yet. At least we might be able to improve that with time. But I think one thing that we can say from the reflection data and the refraction data is that the angle at which this kind of oceanic basement seems to be extending beneath the terrace isn't high enough to get it down below the continental lithosphere. So it doesn't seem like, it might have some under thrusting, but it doesn't seem like it's really a full subduction like slab that's going all the way under North America. Okay. Okay. So I'm going to accelerate a little bit. We're approaching 4:30. We're not that far away. And I'm going to hop now up north again. Okay. So now this is the other zone. This is the Craig, Alaska region, off where we had the magnitude 7 kind of strike slip earthquake. Okay. So I'm going to show you similar images from that zone. So this is now the seismic reflection image. I don't know if this group will immediately think this, but when I first saw this image and I told myself, maybe in the context of what we were just looking at, okay, we know there's this like convergence in the south, there's got to be deformation of the Pacific plate. You know, if some of the images I showed you for that line 3 in the south looked a little bit subduction zone-y, it's like, well, that's kind of amazing, but we do know there's some convergence down there. So we saw that thrust earthquake. As I now pop up to the north, I think it's surprising that we still see some of those same patterns, okay? And so I'll orient here. So this is again the Pacific plate. It's definitely dipping as you approach the Queen Charlotte Fault, okay? And so here's the surface, that really dramatic linear surface of the Queen Charlotte Fault that we can see from the bathymetry. In the seismic data, we were imaging it, but it's certainly not the most impressive deformation feature that we see across this profile. We continue to see a highly deformed continental slope environment. It's not quite as broad of an accretionary prism-like structure as it is way down by the Queen Charlotte Terrace, but it's still interestingly folded. In some places there might be evidence for faulting. We see faulting and deformation, at least past faulting and deformation through offset reflectors on the Pacific plate. So it's really impressive how similar these lines look, in my opinion. Okay, here now is seismic refraction results. Okay, this is from a master's student I'm working at Western, Zara Garza. And so these are just 1D profiles. I have this on the other slide too, if you're kind of curious to compare the velocities. But again, the dashed line is where we think the Queen Charlotte Fault is located. We see kind of a fast, strong continental, like maybe central or lower crust here. But we see the expression of this dipping Pacific plate, and then this kind of broad zone of deformation that's more prominent than the fault itself in terms of like expression of where crustal material has been modified by sort of the tectonics of the region, okay? And so I'm gonna, in the interest of time, I'm gonna kind of wrap things up here. I could go on and on and on about insights from the new geophysics data, but I would probably rather leave time for at least a couple questions and then do that. I do want to though, just kind of leave you with a couple takeaways. Okay, so here back, these are interpretations of margin structure that we can take even just from Geology, and this is the 10 Brink papers. And so if this is sort of something close to what we're seeing in the marine seismic data for the south as compared to the north, I think some of the takeaways that we can make from some of this new data is that the kind of long-term history of deformation, definitely within the Pacific plate, strike slip faulting, as well as thrust faulting and sort of wrench tectonics coupled with convergence on top of them, seems to be certainly important in the south, but continues to be one of the most important kind of expressions of this big plate boundary fault as you work your way to the north even, okay? So even though we're in this like mostly kind of normal strike slip regime up there in the Craig region at the northern end of the survey, we still have a big kind of broad deformed margin. We still have a dipping Pacific plate. And if the Queen Charlotte Fault is at the location of continent ocean boundary, which it seems, as far as we can tell, that it probably is, it's not going to be like a bimaterial interface, like we might have thought if we were looking at really zoomed out, kind of simplified versions of the plate margin. The fact that we have this sort of tectonically modified, deformed section of the plate boundary in between is going to lead to the vertical expression of the fault being kind of a little bit less prominent than that broad scale tectonic expression, the deformation expression. The other thing I'll mention, and I think I have this, so that's kind of what I just said. It's not a bimaterial interface. The other thing I'll quickly mention as maybe the last point is that the fact, so these are actually earthquakes now plotted on top of the fault in the north. These are aftershocks of the magnitude 7.5 earthquake. So maybe they're consistent with a vertical fault that's maybe dipping a little bit to the east, but the fact that there doesn't seem to be a big damage zone that we can image at the resolution of our imaging tools across this 5 centimeter a year plate boundary fault is kind of impressive in of itself. And that could be a result of the fact that strain is just being really efficiently localized along this big important plate boundary structure. But there's not a ton of other deformation that's kind of happening like farther away within maybe a kilometer of that fault, that strain is really localized along this vertical feature here and here. But certainly there has been slip and deformation that's happened at previous times along the margin that's led to this type of deformation structure to the west, sort of within the Pacific plate and the Queen Charlotte Terrace. So I think that's really interesting. And we're still working on this, and I'd love to talk with anybody who wants more details on any of it, more detail. But I'll leave you with this for now and say thanks again for having me.